Hello everyone, this is Manas Ranjan Sahu and I'm here to present my project on DPU learning for OpenAI Gymnasium Lunar Lander V3. So as part of this project, what I try to do is I use the DeepQ network and I use the OpenAI's Gymnasium's Lunar Lander environment to create an agent which can successfully complete all the obstacles that are mentioned as part of this environment. So what exactly are the objectives that it has to fulfill? When you look at the lunar lander environment, it needs that this particular spacecraft could have to land at different terrains, and the objective is that it has to land within these two flags that I mentioned over here. It has to also make sure that it can reach within the solved criteria is 200, so it has to score at least 200 points, and it does face a penalty on the number of steps it takes. The maximum number of steps that are allowed are 1,000. And also it has to make sure that it doesn't use a lot of fuel too. So for each time it uses the main thruster, there is a negative of zero point 0.3, whereas if it uses the side thrusters for left and right direction, then it has a negative of 0.03 points as well. On top of it, when it lands, if it lands between these 2 points, it gets a score of 100. If both the legs touch properly, then they get additional 20 points each, like 10 points each. And if it lands directly in the center, then it gets additional 20 points. So it has a potential of scoring at least 100 to 140 points by reaching within this area. So the benchmarks that I set up for myself as part of this particular project was that I should achieve a mean reward of 220 points, whereas the solved criteria is 200. So I wanted to increase it a little bit more. Then a landing success rate of 95%. Then an episode length, I would like to achieve this proper landing within 250 steps. And as there is a penalty for any time we use fuel, so there is a thruster fuel penalty. I try to keep that penalty ratio at 10% or a maximum of 20 points. Additionally, I also wanted to make sure that we create an efficient system. So I had kept an engine idle percentage of 50%. So I'll try to achieve that it uses gravity to the fullest and it uses the engine only 50% of the time. So those are the objectives that I was started off with. Um, and as you could see that whenever the part of this particular state is such that as this is a continuous environment, each time the environment will provide us with 8 different coordinates. You have the x coordinate, the y coordinate, the x direction velocity or the horizontal velocity, the y direction velocity for the particular lander, the angle of the lander, the angular velocity of the lander, then whether the left leg has made a contact or not, or the right leg has made a contact with the ground or not. The actions that it has are four, which is zero, that means do nothing, let gravity do most of the heavy lifting. Then one is when the left engine is going to fire. Two is when the main downward engine is going to fire. And three is when the right engine is going to fire. So as we discussed earlier, there is a reward for distance, there is a reward for speed, there's a reward for angle, there's a reward for touchdown, a reward for fuel efficiency, and a reward for reaching the lander properly. Okay, so with having said that, what I exactly did is I created a deep Q network where I used I used 8 input nodes, which corresponds to the 8 input points that we discussed right now. That will be connected to two fully connected hidden layers of 128 nodes. And the activation layer for all those fully connected the layers would be ReLU. That will bring in the non-linearity concept as well. So because of the non-linear aspect, it will be able to understand this continuous environment better, and the outputs would be 4 linear output nodes. Now, why 4? Because we have the 4 action items that we mentioned here. So as an output, it is going to provide us with a Q value for each of those action nodes, and then we can decide which one is the maximum among them and then take the action according to that. So that is how the four output would be there. It will find what is the maximum amongst these Q values of the 4 action nodes and then take an action. Coming back to this, we also, as part of this deep Q network, we also created an experience replay buffer. It would have a maximum size of 50,000, but every time what happens is it keeps, whenever it runs, it is going to feed that and get that stored. The experience is going to get stored, and which is going to then get a mini batch of 128 experiences at one time, and that is going to come back and it is going to help it not get affected by any kind of sequential episodes that it runs through. So through the sample min batch, we are able to break any kind of temporal correlation. And if the neural network forgets about what the previous or the older versions were, or what the older scenario and its outputs were, it is going to be able to use that through this mini batch and be able to understand that. Now, additionally, this DQN network agent is going to have a dual network system. What it means is that it will have the policy network and it will have a target network. Initially, both of these would be the same. They would be a replica of each other, but we'll continuously update the target network through what we observe as part of the policy network. Now, this update is going to be very softly done. We only use a 0.005 of blending, so that way only some aspects of some part of the policy network gets mapped into the target network, and so that the training it doesn't abruptly drops. The reason for having this target network is also because we want to avoid any kind of large gradient spikes, and because if we are going to use if you are going to use the same targets from the policy network, they will be continuously changing, and that is how it is going to fail if we use the same policy network as our target. So that the moving target problem is avoided when we are using two networks, one for policy, one for target, as part of this DQN agent. Now, I discussed about the experience relay, about how the batch size will be 128. And on top of it, what we did is, as part of this DQN agent run, during the training, after every 50 episodes, we'll try to take a break and go for a pure greedy selection and use a 20 episode or 20 runs episode of a validation phase. So during that time, whatever we have learned in the 50 episodes of training would be used to see whether we have learned or not within a 20 episode run. So as we incrementally increase our training, the validation episodes or validation runs of 20 episodes keeps on improving as well, which we are going to see as part of our findings too. Okay, now this is overall the agent implementation that you can see here. We are using mean squared Bellman. We are using the Huber loss, which is going to help us in smoothing the L1 loss, and we also use an Adam W optimizer as well. So now, moving on, we were trying to, okay, I discussed about how we are going to do the tau, which is the soft update. Now the training lab. So as part of training, we are capturing a lot of different metrics. We are capturing the training rewards, we're capturing the MS, the Huber one loss, the average Q values, then whether the prediction gap is the difference between the policy and the target. So how much is the gap between these two? We are capturing that. The idea behind this is, as we train better and better, the gap should reduce to zero. I'll try to provide you with a better visual of the evaluation metrics. So these are going to be the evaluation metrics in a single table. So as we discussed, the mean cumulative will be 220. We discussed about episode length. Now, as per as our Q value estimation, we're trying to reduce the prediction gap to zero. So which I was discussing about. The thruster penalty would be like 10% of ratio, which is maximum of 20%, 20 of penalty. And we additionally also try to do some convergence speed. We are trying to find out what is the best hyperparameter as well, which I'll discuss later. Now, after gathering all this, we start the training, and then we also do an evaluation after every 50 episode runs through a 20 validation steps. Now, all these episode runs for training as well as for evaluation, both are all done through seeding. That way, we can make sure that we are able to get the same results every time we run this program. So, okay, so as part of this, as we discussed, we are calculating these different kinds of visualizations. Now, I try to put the visualization in two parts. One is all the training phase visualizations, and then I looked at all the validation phase visualizations. So I'll now go over the graphs where we're going to see some interesting results. So this is the first one, which is a training cumulative reward per episode, and this is during the training phase. Our target was 200, which is the solvency rate, but the target I set for myself was 220. And as you can see, it has exceeded that to close to 250 to 260 as well. Okay. Then this is the graph for the the epsilon exploration decay progression. So this is the exploration and exploitation graph. So we will start off with complete exploration, and as we slowly reduce the epsilon value, by the time it reaches 500 or 550, it reaches 0.1, which is the kind of the minimum of epsilon that we have set for ourselves. So it is going to have only a very minimal of exploration, and maximum it is going to exploit. Then this is the overall Huber loss convergence. Our idea is that Huber loss should be minimized. So as you can see, during the training phase, it started off with around 2 of Huber loss. It reaches to around 3.5. Okay, so between 1.5 to 3.5, it keeps on running through this initial phases, and after 200 episodes, it starts it's decreasing substantially, and by the time we reach around 550, it has minimized to around 0.5. The next is the average Q value. So one thing I would like to just highlight before we proceed forward, just keep a track of this episode values, which is 450, and then 500 and 550 and 600. So anything above 450, you will see a much better stabilization in the results. So which is also you can see over here. As you can see in 450, it started to stabilize and then even reduce much further as well. Similarly, over here in average key value, you could see that the key value increased and decreased. So there's a lot of variance between these. The variance continues, and after 450, it plateaus. So you have a steady state key value as well. The next is the prediction gap, which I discussed that the difference between the policy as well as the target value of Q. So as you can see that we had a huge variance in initially, it reduced much below the zero and then slowly increased, and then it was going parallel to the zero and pretty close to the zero value. It was not exactly touching zero at all the times, but in some instances it was touching, and it maintained kind of like a plateau after episode 300. The next is during the training phase, we wanted to understand how much is the engine idle capacity. That means how much time action zero is being used. That means how much time the lander is letting the gravity do the talk. So over here, you can see that our target was 50%. We wanted 50% of time no engine should be fired. It tried to reach 50% in many cases, sometimes even reaching the 60% mark. But when you look at it on an average level, it was around 35 to 40% of the time. It was in that particular range. So what we could understand is that the agent tried to create a balance between successfully landing and fuel efficiency. So even though it had a higher negative mark, it could counter that through the overall scores that it got. That means successfully landing between and both the legs landing, touching the ground, as well as landing in the center. So it was able to achieve, and by that way, it could counter this negative points that it could get from the engine fuel usage as well. So same thing as I was talking about in the previous slide. Our target was we do not want to spend more than 20 points in terms of penalty because of fuel usage. So there was a huge frantic use of fuel initially because it was learning, and after it kind of learned after 300 episodes, it was properly understanding how exactly to perform. You can see that the fuel usage reduces, and as we go towards 450 onwards, it has kind of like plateaued. So yes, our fuel usage was still there. We were not able to meet the 20 point of penalty that we had set our targets are for ourselves, but we could see that it was not too high as well. It was below 50 throughout, and that actually helps in understanding that okay, the agent was trying to create a balance between the penalty and the overall score. So it was able to understand that by getting a better score overall, by making sure that it lands properly in a centered manner, it could still counter any kind of negative penalty point that it gets through usage of fuel. After those graphs, now we come to the validation graphs. So as we discussed, the validation was done like after every 50 episodes of the training run, we had a 20 seeded episodes of the validation run. So as you can see here, initially as the validation was continuing, it was not able to understand that, and it was also exploring. So because of that, you could see that it starts off with close to 150 negative points, but as the training progresses, it substantially and very accelerated manner it increases the points, and by the time we reach 350 episodes, it has already reached the projected target, which is 220. If you look at the solved case, it has reached that a little before that in around 330 episodes itself. So now after 350 episodes, it goes even higher than 220 benchmark, and by the time we are reaching the 550 episode, it is around 270. So we are beyond the solved status of 200, and we have even reached our 220 project benchmark and reached around 270 as the final scores. Similarly, when we look at the landing success rate, after 350 points, it was around 70%. Before it was kind of zero, it was not able to land, and it starts off scoring some points on landing from 250 episode onwards. And at 350, it was around 70%. Then it reaches the 95% target that we had set up at around 500, episode 500. And from episode 550 onwards, it has 100% landing success rate. Then the overall episode length, as you could see that initially we discussed that how it could not land, and that's why you could see that the overall scores were very low. The landing success rate was very low. So even so here it could here, this is an instance where it could have crashed, okay, and that's why the number of episode length is low. Whereas in these instances like this and this, it kept on hovering and trying to find the best way to land, but it maxed out on the 1,000 steps limit, and that's how the simulation ended here. But then after 300 episode, it understood how exactly it has to do that, and then slowly you can see that the number of episode length decreases drastically, and it reaches our benchmark of 250 at 550 episodes. And between from 550 to 600, it stays within the 250 to 300 mark. So we can see that yes, it has significantly achieved success. It is able to meet the benchmarks as well. The next is the engine idle percentage. We had set ourselves with a benchmark of 50% for engine idle percentage, but as you could see that it was trying to create a balance between successful landing, getting the maximum points, and still not using a lot of fuel. So as you could see that our overall engine idle benchmark, even in the validation phase, is between 35 to 40%. So it was not able to meet the 50% mark, but it kept within the 35 to 39% mark throughout. The next would be the thruster fuel penalty. So as we discussed, there is a fuel penalty when you use it, and our target that we had set ourselves for was only a negative 20. We could not achieve that, but I would be happy to say that it is not that worse. It did not perform that bad. It was able to stay within the 40 to 42, 45 negative points throughout this validation scores. And from 450 episode of training run onwards, when the validation that happened after 450 episodes were run, you could see that it has been steadily within this kind of like a plateau of 40. So even though we did not reach the 20, it was a little bit more than 20, which is 40 in this case. The next is all the interpretations, which I kind of already discussed and talked about on the call by while showing you the graphs. And after that is done, we also try to do hyperparameter analysis. So while we got this successfully done, we also tried to do a study with two different other configurations through a 300 training episodes. So this is our baseline configuration, which we already discussed here. We also tried to use the high learning rate, and in this case, a 10x high learning rate. We used alpha at 10 to the power minus 3, and try to see if we have a very aggressive learning rate, is the agent able to perform better. We also did a slow soft update. So while we discussed about how we want a 0.005 of update, we wanted to reduce that and make it 0.001 and see that if it's a 5x slower target network synchronization, what is the effect that it gets. That means it is the target network is going to get updated pretty slower. Whatever the policy network is understanding or learning from its training run, it will be translated very late to the agent. And we wanted to see what is that effect within the 300 training episodes. Now we created a function to run that, and then we ran it, and this is the output as part of that. What you could see here is that this is our baseline, the green one, and you could see that it has steadily kept on increasing, and it has reached the 100 score as well. It has reached the 100 score, even though the overall target score is 200, and we already saw that around 500 episode is when it reaches that. So because we are running it for only 300 episodes, we could see that it reached the score of 100 at the end of it. Now, when you look at our high learning rate, you could say that because of the high learning rate, it's actually exceeds the baseline initially and at other points as well. So here you can see there are many places where the high learning rate actually exceeds the baseline scores. But let's say around 240 mark, it has a score of around 70. And after that score, it substantially reduces. So it reduces, and by the time we reach the 300 episode mark, it's stagnant at around 50. So because of gradient overshooting, which happens in case of high learning, it reduces, and finally the score is much below the baseline score of 100. Now, the third item was the slow soft update one. And as part of it, when you look at, there is a conservative update of the target network. It performs poorly initially. So here you can see it is much below the baseline and the high learning rate graph. It is still below, but after around 140 or 120 episodes, it suddenly jumps up. It and all that learning that it was capturing through all this different episode, it suddenly gives a big jump and exceeds both the high learning as well as the baseline learning, and continues through that. But again, suddenly after episode 200, it drops and goes below both the curves. It continues through that, and then suddenly around 240 episodes onwards, it suddenly gets a big jump and even exceeds the baseline number. So you could see that there's a lot of variance in how the the slow soft update performs. There's a huge variance, even though it exceeds. The variance is something of a concern. Okay, so what we could understand is that if we want a reliable network, the baseline hyperparameter options that we selected is the much stabler one, because it doesn't have any gradient of overshooting, and it doesn't have a lot of variance as well, which we could see in the other two curves that we could see. So this is what our overall project was. We could overall achieve the environment solvency. We achieved a score of 270 on our baseline network across the 600 episodes that we ran. We could also see that beyond 550 episode onwards, we had 100% of landing success rate. And we could also create something that has a very decent low engine idle rate of 34 to 39%, and a fuel penalty, a maximum of 40 points. So we were able to get a great stability, a great optimized network created through this overall project. And in our hyperparameter sensitivity, as we discussed, we ran through the three different options, and we could see that our baseline option actually performed much better. It did not have any gradient of overshooting, or it did not have a lot of variance as well. So with that, I would like to conclude my presentation for this project. I hope this was helpful, and I hope this makes you understand an application of DQN network and how it could be useful in a continuous state environment. Thank you.